Welcome back to another Explainer. Today, we're diving into a really fascinating collision between cutting-edge technology and a century-old medical challenge. You know, for well over 100 years, we've relied on humans actually peering through glass lenses to diagnose one of the world's absolute deadliest diseases, malaria. But what exactly happens when we automate the microscope and literally teach a machine to see? Well, that's exactly what we're going to unpack today. Because it all starts with this staggering problem. How do you accurately diagnose over 260 million clinical cases of malaria every single year, especially when your frontline experts are just exhausted? It's this massive human limitation sitting right at the absolute core of global health diagnostics. And honestly, it requires a revolutionary answer. Section 1. The microscope bottleneck. Let's look at how we've traditionally diagnosed this disease and why it's currently straining our medical systems. The scale of this disease is just daunting. In 2023 alone, malaria caused over 260 million clinical cases globally. Think about that number. And despite all our modern medical advancements, the standard diagnosis still relies incredibly heavily on a highly manual process. We're still depending on a real person preparing thick and thin blood smears, staining them by hand, and physically examining them under a light microscope.
As researchers point out in our source material, the major drawback of this approach is its dependence on skilled technicians, of which there's a critical shortage. The disease is spreading, sure, but the real bottleneck isn't just the parasite itself. It's the sheer lack of trained, rested eyes available to actually look for it.
It's kind of like looking for a needle in a microscopic haystack over and over again. On one hand, you have the manual burden. A single mass survey smear might require a technician to meticulously observe 500 to 1,000 individual blood cells. On the other hand, you've got the human cost, intense physical and mental fatigue. When you're staring down a lens for hours on end, exhaustion sets in, and that leads to delays and, tragically, inaccurate diagnoses. Plus, the varying appearance of the parasite at different life stages just makes this visual marathon even harder.
Section 2. Enter artificial intelligence.
So, to understand how this tech works, we need to quickly define deep learning. Basically, it's an artificial intelligence technique where systems analyze massive amounts of data, in this case, microscopic images of blood, to automatically detect patterns. By feeding an AI thousands of these images, the machine effectively learns how to see and identify parasites, much like a human technician does, but with one major difference: it never gets tired.
Enter devices like the Now Lab. This is a fully integrated, automated microscope designed specifically to tackle this diagnostic bottleneck head-on. Now, it's really important to view this not as some robotic replacement coming for healthcare jobs, but rather as a tireless, unrelenting assistant. It's exactly what the medical field desperately needs right now.
So how does this actually work in practice? It's an incredibly streamlined process. First, the operator loads just 5 microliters of blood into a disposable cartridge. Next, the machine automatically prepares and stains the smear internally. Literally no manual human intervention required. Then it images an astounding 200,000 cells. And finally, the AI algorithm scans those digital images to detect any parasites.
And here's the kicker. It does all of that in about 15 minutes. That speed is absolutely crucial. You're getting rapid results for the patient while completely removing both the physical labor of preparing the slide and the visual strain of scanning it.
Section 3. Testing in the field. Because AI might work in a pristine lab, but malaria happens in the complex real world. A recent massive study rigorously stress-tested this exact technology. Researchers collected 2,201 samples from febrile patients across clinics in Ethiopia and Ghana. These are areas where malaria transmission is intense, and in Ethiopia's case, where multiple species of the parasite are co-endemic. They compared the AI device directly against top-tier expert human microscopy and molecular PCR tests.
Now, what's truly staggering here is success rate. Using expert human microscopy as the gold standard, the automated AI system achieved a 96.3% sensitivity for detecting Plasmodium falciparum and a 96.8% sensitivity for detecting Plasmodium vivax. So the AI is effectively matching the accuracy of the most highly trained human eyes in the world. But it actually gets even better. The AI device successfully detected 47 positive infections, which were later confirmed by highly sensitive molecular PCR tests that the human expert microscopists missed completely. Let that sink in.
It's not just matching humans, it's catching the very subtle infections that even the best but inevitably tired human eyes occasionally skip over.
Section 4, the Indonesian AI model. This is a global movement, too. Researchers in Jakarta at Indonesia's National Research and Innovation Agency, or BRIN, have been developing their own AI diagnostic tool. They train their algorithm using a massive local dataset of 1,388 blood smear microphotos collected directly from malaria endemic areas in Indonesia. Essentially, they're tailoring the AI to their specific local parasite variations.
If we look at their early testing metrics, the results are incredibly promising. The system achieved a sensitivity of over 84% in distinguishing between healthy and infected cells. And crucially, it hit an overall accuracy value, or F1 score, of 80.60%. This shows a really high reliability in correctly identifying both the specific parasite species and their life stages.
To get those results, the BRIN AI rapidly analyzed 3,362 individual cells across 35 real-case micrographs. Just imagine a human counting and analyzing over 3,000 cells one by one. The AI accelerates this highly tedious process dramatically, all while maintaining that crucial baseline of accuracy.
Section 5, a new diagnostic era. We've seen the tech and the data, but what does this actually mean for global healthcare?
The ultimate benefits here go far beyond just saving time in a lab. First off, it enables remote diagnostics in underserved areas. You can place this device in a rural clinic, and suddenly they have world-class diagnostic capabilities. Second, it retains expert knowledge to aid staff who might have limited training. The expertise of top parasitologists is essentially programmed right into the machine. And third, it facilitates rapid mass field surveys, which allows public health officials to screen huge populations quickly to control disease outbreaks.
So the crucial takeaway here is this. AI isn't replacing healthcare workers, it's empowering them. It provides a tireless partner that ensures diagnostic accuracy no matter how long the shift has been or how many slides are waiting in the queue. It bridges that massive gap between the staggering volume of cases and the very limited number of human experts.
Which leaves us with this final thought. We're seeing artificial intelligence successfully prepare, stain, and identify different species of the malaria parasite in just minutes. If AI can master something as complex and devastating as the malaria parasite, what other microscopic threats will it conquer next? Thank you for joining me for this explainer. I really hope this helped you grasp exactly how automated microscopy is changing the world. See you next time.